Today we're going to talk about congruent chords. So the theorem that we're going to be working off of is that two chords of a circle are congruent if and only if they are equidistant from the center. So you might notice the kind of odd phrasing of if and only if in this sentence. If and only if is actually a math term or a way of saying things when you're presenting a math theorem that has a very specific meaning. So what it means is if I were to write like A, if and only if, and IFF is often the notation you'll use for that. A, if and only if B, this means two things. It means that A is true if B is true, and it also means that B is true if A is true. So it means that this statement is true in both directions, so to speak. Two chords of a circle are congruent if they're equidistant from the center, and two chords are equidistant from the center if they are congruent. Okay, so that's what that means there, if and only if. So let's look at why this is true. So we're claiming that chord CD should be congruent to chord BA if they're equidistant from the center. So if I say that these are the same distance from the center, then these things should be congruent. Well, I know from what we talked about last time that this is a perpendicular bisector, and that this little bit here is congruent to this bit here, and this bit here is congruent to this bit here. And then what I can do is I'll use a different color for this. I can do a triangle like this, 4 triangles. And now I can say, oh, hey, look, side angle side, side angle side, side angle side. These are all the same triangle, right? Which means that this is equal to this, is equal to this, is equal to this, and therefore this chord is equal to this chord. Okay, so again, we could do the proof in the other way too, where if, instead we started by saying they're congruent. If these two things are congruent, then we can prove they're equidistant. It's the exact same argument, right? If they're congruent, you can still draw the same triangles, and you just show that these sides are the same instead. So let's look at some example problems. Let's do problem like this. So I have a circle, and what we're being given is it's a circle with a center at O. Chord AB is congruent to chord CD, and I'm given some distances here. So I'm told that OP, so this little distance here, is equal to 12x minus 5, and OQ, so this distance here, is equal to 4x plus 19. And I want to find the length of OP. Well, I know that if these two chords are congruent, which is given to me in the givens, then they must be equidistant from the center, which means that 12x minus 5 must be equal to 4x plus 19. So I can set this up, 12x minus 5 equals 4x plus 19, and then I can solve for x. And if you solve for x, you should find that x is equal to 3. But remember, we're not done, because I want to find the length of chord OP. I'm not looking for what x is, so I got to plug that in. So OP is going to be equal to 12 times 3 minus 5, which is going to be equal to 31. Okay, so that's how we could use the theorem for this first problem. The second problem here, a little bit more of a complex setup here. So I'm told that triangle ABC is an isosceles triangle with base of AC. Okay, so what that means is that chord AB is going to be congruent to chord BC. I have a circle that's centered at P. I know that PQ is perpendicular to AB, and I know that PR is perpendicular to CB. So I'm going to draw some stuff on here before I try to prove anything. And what it wants me to prove is that this triangle here is isosceles. Okay, so here we go. So ABC is isosceles with a base of AC. So that means that this side, AB, right, AB is going to have to be equal to BC. And then I can say, well, if these two things are equal, I have two chords that are congruent, that means that they must be the same distance from the center. And I'm also told that PQ is perpendicular to AB, PR is perpendicular to CB. So this is a right angle, this is a right angle. They're perpendicular from the center. These distances must be the same. This is therefore, by the definition of an isosceles triangle, an isosceles triangle. But we're going to write this out in proof form, because it's a good skill for you to have. So first statement we're going to make is that all of our givens, right, or most of our givens, we'll split them into two parts. So I have a circle centered at P. I know PQ is perpendicular to AB, and PR is perpendicular to CB. And the reason is because that's a given. Second, I'm going to list the rest of my givens, which is that triangle ABC is isosceles with a base of AC. And that is also a given. For 3, I know that chord AB is congruent to chord BC. How do I know this? Well, I know that if two chords are congruent, I know it because it's an isosceles triangle. I'm skipping ahead. Just from the definition of an isosceles triangle. Isosceles definition. The fourth thing I can write is I know that PQ is going to be congruent to PR. And this comes from our theorem, right? Is Congruent Chords theorem. Because two chords are congruent, that means they must be equidistant from the center, and the distance from the center is PQ and PR. So those things must be the same. And then finally, we can say that triangle PQR is isosceles because of the definition of isosceles. Two sides are congruent. Isosceles definition. Okay, so there you go. That's how you can apply congruent chords to solve some problems, and it's going to be an important thing to keep in mind as we go forward. Thanks for watching.